In this video I'm going to think about what is required to disprove a statement, because sometimes it's actually much easier to prove that a statement is not true than that it is true. And so we need to think about what is required to be sure that we have disproved something. And the first thing we need to think about is what is the statement actually saying this particular thing is true for? Is it saying it's true in all cases? Or is it saying it's true just in specific cases? And so to do that, we need to define two types of what we call quantifiers. The first of those is the universal quantifier, which is saying for all cases, or for every case, or for each case. And we do have a mathematical symbol for that, a sort of upside down capital A. So let me give you an example of that. For all x, which are elements of the set of natural numbers, x squared is greater than or equal to x. Or another way of saying that would just be to say, for every natural number, x squared is greater than or equal to x. Now that may be true, that may not be true, but that is an example of a universal quantifier statement. Using the mathematical symbol, we could write that in that way there. For all x, which are natural numbers, x squared is greater than or equal to x. Our other type of quantifier is what we call the existential quantifier, which is saying there exists. In other words, there's at least one case. There exists at least one case where this statement is true. So an example of that would be there exists a real number x such that x squared is smaller than x. In other words, there exists at least one real number such that the square of the number is smaller than the number itself. Or using that sort of backwards e as the symbol, we could write there exists a real number x such that x squared is less than x. Alright, so having defined those two types of quantifiers, now I want us to think about what we might need to do to negate a statement which involves one of these quantifiers. Now I'm going to go through this, and if you need to sort of pause the video to think about the statements I'm making, then do that. So we need to swap the type of quantifier that we're using if we're negating a statement. In other words, if we're trying to negate a for all statement, we need to negate that with an existential quantifier. So here's the first example. The negation of the statement for every natural number n, or for all n which are elements of the set of natural numbers. Okay, for all natural numbers n squared is greater than n. If we were trying to negate that, the negation of that is not for all natural numbers n is less than n squared, or rather n squared is less than n. It's just for at least one case. So the negation of that is there exists a natural number n such that n squared is not greater than or equal to n. N squared is less than n. So notice if we're negating a for all statement, we just need to find one example of where it's not true. Likewise, if we had an existential statement, so the negation of the statement there exists a natural number such that 4n minus 1 is prime. Okay, if we want to negate that, we would be swapping the quantifier and saying for all natural numbers n, 4n minus 1 is not prime. So think about that one for a moment. There exists a natural number such that 4n minus 1 is prime. We don't need to show that there's just a single case where it's not prime. If we're going to negate that, we need to show that in every case it's not prime. Alright, if you've sort of got your head around that, let's think about the implications, and I've sort of explained those. So it follows that to disprove a for all statement, a universal statement, we simply need to find one single counterexample. If you tell me that this always happens, that it always rains on the 1st of January, I just need to find one example of when it didn't rain on the 1st of January, and I've disproved your statement. To disprove a there exists statement, an existential statement, we need to prove its negation. Now maybe that one's a little bit harder to get your head around, but let's do a couple of examples and hopefully that will help. So I'm going to grab a couple of questions from the textbook, from the exercise, and let's see if we can make sense of each of those. So firstly, we've got a question here where it says for every natural number n, the number 2n squared minus 4n plus 31 is prime. So the statement that's being made is that for all natural numbers n, what is it? 2n squared minus 4n plus 31 is prime. And we want to try and prove that's false, and because it's a for all statement, all we need to do is find a single counterexample, a single case where that is not true. Now, of course, you could start from n equals 1. I mean, the natural numbers are 1, 2, 3, 4, 5, so we could try 1 and 2 and 3 and 4 and 5. It might take us a while to get to a counterexample, but in fact there is one obvious counterexample if you think about that number, because obviously whatever we choose for n, the first two terms will have a factor of n, so it's really just the third term here that we need to sort of ensure has a factor of the natural number, and 31 has a factor of 31. So as our counterexample, let's let n equal 31, because then 2n squared minus 4n plus 31 is equal to 2 lots of 31 squared minus 4 times 31 plus 31. And we could write that as 31 outside of, 2 times 31, so that's 62 minus 4 plus 1. And even in that form there, we can see that it already has a factor of 31, doesn't it? Or we could write it as 31 times, what's that, 63 minus 4 is 59. And that is clearly not prime, is it? Because it has two factors other than 1 and itself. Alright, so we found one counterexample. That is enough to prove that that for all, that universal statement is not true. Alright, one more example then. Let's go question 5a. So in this one we're trying to show that each of the following existence statements is false. So this one says there exists a natural number n such that 9n squared minus 1 is a prime number. So let's write that using our there exists a natural number n such that 9n squared minus 1 is prime. Alright, so again, we could take a while here. We're trying to just find one single case, one single natural number n such that 9n squared minus 1 is prime, and so you could sort of start from 1 and 2 and 3 and 4 and try and find that single case. But we might sort of come to the conclusion fairly soon that we're not finding one, and so maybe it's not true. Maybe there is not a single natural number n such that that's prime. So in order to disprove that statement, we could try and prove that actually for every natural number 9n squared minus 1 is not prime. Okay, that it's always not prime. So let's try proving that for all natural numbers n, 9n squared minus 1 is not prime. Because if we do that, then we've disproved that there exists an n where it is prime. Okay, well for this one here, if we recognize that expression there is actually a a difference of two squares, so it's the difference of what, 3n squared and 1 squared, then we can factorize it as 3n minus 1 times 3n plus 1. And really for all natural numbers, so 1 is the smallest natural number that we have, so the smallest factor that we can get out of this would be 3 minus 1, which is 2. So therefore, in every single case, this natural number, or these numbers, are going to be greater than or equal to 2. So let's say since 3n minus 1 is greater than or equal to 2 for all natural numbers n, therefore the product of those two numbers is going to be 2 times something bigger than 2, and therefore 9n squared minus 1 cannot be prime, because, just to emphasize that, because what we're saying is that this here is going to be the product of 2 and some other integer larger than 2, and therefore that is not a prime number. Okay, and so by proving the universal statement, we have disproved the existential statement.